This is the Honda Civic. You have probably seen this car nearly every time you drive, but what you may not have seen is the source behind this vehicle's renounced reputation for reliability, performance, and efficiency. Meet the K20C2. The K20C2 is a 2-liter naturally aspirated 4-cylinder engine that is designed for efficiency, longevity, and real-world performance. Understanding this engine helps reveal the engineering behind a car most people take for granted. In this video, I'll be discussing the different systems and specifications in the K20C2, including the combustion chamber design, the fuel delivery system, the ignition system, the valve train and cam, the intake and exhaust, and also calculating boost pressure to double the engine's power. The K20C2's combustion chamber has 1,996 cubic centimeters of displacement with a bore of 86 millimeters and a stroke of 85.9 millimeters. This yields a compression ratio of about 10.8 to 1, which helps ensure the engine runs smoothly no matter the speed. For fuel delivery, this engine uses a multi-point injection system that sprays fuel into the intake ports at low pressure. It has an air-to-fuel ratio of 14.7 to 1. Each piston has a singular center-mounted spark plug with a shorter flame distance and more uniform pressure rise. The K20 has nylon-reinforced polymer fuel lines and a stainless steel high-pressure fuel rail. Combined with an aluminum alloy engine block and pistons, this engine has a peak output of 158 horsepower at 6,500 RPM and a torque of 138 pound-foot. Looking at the valve train and cam, the K20 uses a dual overhead camshaft with 4 valves per cylinder, totaling 16 valves. Both the intake and exhaust camshafts are mounted into an aluminum cylinder head and actuate the valves through roller rocker arms. The cams are made out of high-carbon, high-chrome cast steel alloy equipped with Honda's VTEC technology or variable timing exhaust control. In Honda's VTEC engines, the intake camshaft has 2 different lobe sizes, 2 standard size outer lobes and a large center lobe. At lower RPM, only the outer lobes are controlling the valves. As the engine begins to spin more quickly, the center lobe takes over and the valves open sooner and close later. This results in a sudden burst of speed and better performance. The K20C2 is naturally aspirated, drawing air into the cylinders using only atmospheric pressure at the intake shown here, which sends the air into the intake manifold. The intake manifold is composed of glass fiber reinforced plastic composite with Helmholtz-style resonator chambers for noise reduction and ducting made of rubber reinforced polymer. At peak power, the K20C2 intakes 200 cubic feet of air per minute. The exhaust manifold, located here, is made of aluminum with internal exhaust passages cast directly into the cylinder head. Next, I'll be calculating how much boost pressure will be required using a supercharger without an intercooler to double the K20C2's engine power production to 316 horsepower. This is assuming isentropic compression of the intake charge.
To calculate our desired boost pressure, we first start off with the power equation for our engine. Since the only thing we are changing in our engine is the actual intake boost pressure itself, we can only focus on the part of the equation dealing with the amount of air that comes into the engine, which is here. Next, we make our assumptions. We assume that atmospheric pressure, or P1, is 101.3 kilopascals. We assume that K, or the ratio of specific heats, is 1.4. We assume that doubling density equals doubling the power, and we also assume isentropic compression. Next, we use our density ratio for an ideal gas and set it equal to 2 for double power. We then take our isentropic temperature relation and put it in the terms of T1 over T2, in which we can combine like terms in our density equation for double power. Now we can solve the resulting equation by raising both sides to the power of k and plugging in our values for P1 and k to give us P2. Finally, we can take our calculated P2 of 267.4 kilopascals, subtract it by our given value of P1, 101.3 kilopascals, to give us our required boost pressure of 166.1 kilopascals. Overall, the Honda K20C2 shows how thoughtful engineering can turn a simple, everyday engine into an efficient and reliable power plant. Thank you for watching.